All right, welcome back. In this lecture, we're talking about particle kinetics, and in particular, we're talking about the impulse and momentum method. This method is really good anytime you are analyzing kinetics of a dynamic system over a particular period. So you're looking at change over time. And this method is really good at that. With some of the previous methods, such as the work and energy method, those are better at calculating change over a given change in displacement or change in position, whereas this is better for a change in time. Okay, so we've established that. So how does this work? Well, we need to start with the Newton's second law, which is sum of forces is equal to mass times acceleration. This can be written as mass times change in velocity, and then we have dv over dt. So what can be done now is to move the dt over to the left-hand side and to integrate, which will give us something that looks like this. All right, so this is a fundamental equation we've arrived at, and this is commonly referred to as the principle of linear impulse and momentum. So I will put a rectangle around this because it's so important. There it is. And as we said, this is the principle. Okay, so there are multiple components to this equation that we need to look at. And I want to go about this by going from left all the way to the right. So on the left-hand side, we have an integral that's looking at the sum of integration of forces over time. So another way of thinking about this is by looking at it schematically. So let's see. If we have some kind of force over time, the area that's underneath this force time plot, which is also how this integration is operating, is what's commonly referred to as impulse. So this is impulse, and if you have multiple forces being applied on your dynamic system, then you have some of these integrations, right? So this is in fact our impulse, and in this case, it's a single force, and we could say it's F dt. And so if your force is a constant, so if it's like a flat surface like this, then it simplifies to F constant T2 minus T1. And of course, T2 is commonly sometime ahead of T1. So it would be something like this. So let's do an example now involving the calculation of coefficient of kinetic friction. So in this example, we have a ski slope. Let's see. We have a ski slope that looks like this. This angle here is given as 60 degrees. We have a skier that is sliding down, and the skier is wearing their skis. The other important features of this problem are that the skier starts at a velocity of 0, and it achieves a velocity of 25 meters per second at approximately 3.5 seconds. So that's the time that's actually in the brackets. This skier is said to be 50 kilograms. And let's see, we have given the angle, and that's really all we really have. And the question is asking you to calculate the mu k, which is your coefficient of kinetic friction. Okay, so the best way to go about this is to break the problem down into the horizontal and the vertical directions. And by horizontal, what I mean is in the tangential direction to the direction of motion, and in the vertical direction. So kind of like this. So these are the positive coordinate systems. So looking at this in the vertical direction, let's say this is a plus. What we're doing is we are looking at the static equilibrium that we have in this direction. So if we have the skier summarized into a particle. We have a 50 kilogram mass, so W is 50 times 9.81, right? That's 9.81 meters per second squared. This gives us a value of 490.5 newtons. We have this being applied at an angle of 60 degrees. This angle is taken from the slope of the ski surface. So then we have a normal that is orthogonal to the slope of the surface. We call this the n. And what we have to do now is to simply calculate n. And an easy way of doing this is basically saying n is equal to w, and then we have to look at the 60-degree components of that w, right? So you have to do cosine 60. And so we have 50 times 9.81 cosine of 60, which is approximately 245 newtons. Okay, but we aren't done. In this free body diagram, we have another force that we've missed, and that's kinetic friction force. So I can use a different color and draw it here as the blue arrow and call this the kinetic friction force. This is always counteracting the direction of motion. So if your skier is going in this direction, so that's your velocity, friction's always acting in the opposite direction. Okay. So then what I can do is I want to analyze in the tangential direction to the slope. So let's say this is a positive, and I can use the principle of impulse and momentum. So my equation is and if we say that the friction force is in the horizontal direction to the slope, in the tangential direction to the slope, then what we have is we have the horizontal component of dw, right? And this is sine 60. So we're looking at this component. And then you have to subtract that from f, or subtract f from that. So that's your total f. Then you have to also account for the period of time over which this force is being applied. And the question told us this was 3.5 seconds, right? We obtained our velocity over 3.5 seconds. And we could say mass is 50 kilograms, 50 kg. Velocity 2 was given as 25 meters per second. And mass times velocity 1 is 0. Velocity 1 is the original velocity with which we started, and that's a 0. So that's all. We have one equation, one unknown, and if we solve this, we get a friction force that is equal to 67.2 newtons. And so the question was asking us for the coefficient of kinetic friction, which is mu k. And this is commonly just calculated as F, friction force, divided by the normal force. So we already know what both of those things are, and we get 0.275. And that's it. Another important concept when it comes to impulse and momentum is whenever you don't have forces being applied on your dynamic system, that's where you get this concept of conservation of linear momentum. So if we look at the equation of impulse and momentum, which was something like this, the assumption with the conservation of linear momentum is that forces no longer exist. So you have a system that doesn't really have external impulses acting on it. So this whole component becomes a 0. And so the right-hand side can be generalized into the following. We have sum of masses, each having an index, vi1, so their original velocities, and sum of those masses times vi2. And of course, for every mass, you have a different index, right? If mass 1 is index 1, mass 2 is index 2, and so forth. We're not done yet, though. Another component to conservation of linear momentum is having to do with impact. because masses can bump into each other, and very often linear momentum is used to analyze various features of impact. So let's say if we're looking at impact, we might have two masses arriving at this horizontal plane, which, by the way, is commonly called the plane of impact. That's our plane of impact. We have mass A going with the velocity v a1. We have mass B going with a velocity of v b1. At the moment of impact, they both arrive at this plane, so they're sort of their surfaces are tangential to the plane of impact, and then they go their separate ways. And you can say the final velocities are VA2 and VB2, kind of like this. So with impacts, there is generally another equation that we look at, and this is called the equation for the coefficient of restitution. So coefficient of restitution. And the way this equation works is it's looking at how your relative velocities before and after impact basically change. So E here is relative velocity at separation. And this is divided by the relative velocity at approach. So this is when the two masses are approaching each other right before impact. This is approach. So what this equation is doing is it's capturing the amount of energy that is lost due to impact. Because obviously, if you've ever bounced a ball and let it just dissipate in its vertical height gain, you will see that it's gradually dropping in height. And that has to do with the amount of energy that's dissipated via either sound or some of the internal forces or some of the other heat loss mechanisms, right? Kinetic energy gets converted into heat, it gets lost. So within this context, we could say if E is equal to 1, then you have an elastic impact. So your relative velocity between approach and separation are completely conserved. So this is elastic impact. And if E is equal to 0, then what it means is that you have velocity coming in, you have no velocity going out. So the two masses are sticking together, they're glued together. And I guess a more scientific way of calling this is plastic. So that's your plastic impact. So let's do an example that looks at all these problems and also connect the conservation of linear momentum with the conservation of energy. So it's a pretty good example. I like to use it. So let's say we have an example, and in this example, we have a baseball arriving at a velocity of 40 feet per second. This baseball has a weight of 0.3 pounds. So it's arriving horizontally and it hits this. Well, let's move things around a little bit so we have a little bit more room. Okay. And so this hits horizontal looking block that looks like this, that is hung from a cord. And this cord is fixed at the base. The block here is 5 pounds and it is still. So think about the process. First, baseball arrives, so it's approaching. It hits the block B. Let's call this B and this is A. Block B then moves. So you have initial momentum getting converted into some kind of final momentum. So you have conservation of momentum. Right? We don't have any other forces. We just have initial velocities and some sort of final velocity. Once this second mass moves, then you have this cord being pushed back into this region of angle theta. And so you have mass B going up in elevation. So it's kind of going up in elevation as a result of that initial velocity that is gained. So think of this as kinetic energy getting converted into potential gravitational energy. So this is also a problem involving conservation of energy. So let's do the first part of the problem. And before we go, I want to make sure we have every bit of information. Oh, see, E here, the coefficient of restitution here is given as 0.6. And this can generally be approximated if we know what the materials are that are going to be impacting each other. Okay, so first of all, we know that WA is 0.3 pounds. We also know that WB is 5 pounds. Those are given to us. Then we have conservation of momentum, which is as follows. We have MA VA1 plus MB VB1. So we have this kind of layout. And what we have to do is we have to plug in all the known and unknown information we have. So let's say we have 0.3 divided by 1g, right? This is multiplied by 40 feet per second. We can kind of ignore MB/VB1 because VB1 is at rest condition, so the velocity is 0. MA/VA1, we don't know what VA2 is. So this is basically 0.3 G VA2, and we have 5 G, and this is VB2. So those are the two velocities that we don't know. So this is one equation, two unknowns. What I'll do is I will take this equation and simplify it just a little bit. So we have 0.3 VA2 plus 5 VB2 equal to 12. So let's call this equation 1. It's one equation, two unknowns. We need a second equation to complement this. Now, using the coefficient of restitution, we have 0.6 is equal to VB2 minus VA2, and then we have VA1 minus VB1. VB1 is 0, VA1 is known, and we get something that looks like this. And we call this equation 2. So now we have two equations, two unknowns, and solving them together should give us the following answers. We have VA2 is equal to minus 20.37 feet per second. This is minus because the assumption when we put the conservation of momentum equation together was that this was a positive. So you always need to maintain the directionality of the velocity vector. And then VB2 is also 3.62 feet per second. So that's really what we have. Next, we have to look at the second part where mass B gains a velocity and it goes up in elevation. So we have a situation where you have, so this is part B, right? Let's make sure these are labeled, part A, part B. So you have a situation where you begin with position here. This is mass B, and then mass B goes up. And I suppose this angle might be sort of exaggerated slightly. So you're converting your VB2, which we calculated just now, into some sort of H max. And we want to know how high this mass goes, but we want to express it in terms of theta. So we want to find out what is theta max. That's really the question here. So let's write the equation for conservation of energy, which is T1 initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential. So what's T1? It's 1/2 mv squared, right? So we have 1/2, mass is 5 pounds divided by 32.2 feet per second squared. V squared is 3.62. This is the value we just discovered. we're going in height. So what I can say is that my datum is down here where my original position was. So then my V1 is equal to 0. So plus 0, and then we have equal. Now we have to look at the right-hand side. As the mass goes up, it gains elevation and it loses velocity until it reaches maximum elevation and it loses all of its velocity. So your kinetic energy at T2 is 0. And then you have mgy. Y here is kind of interesting for V2. Y needs to be expressed in terms of theta instead of H max. So let's say we're looking at H max. Originally, when it's down below, it's 3 feet, right? Or I guess when it's down below, it's just 0 feet. Then we have to somehow express it in terms of the 3 feet of chord length, which I, my apologies, I didn't write at the beginning of the problem. The way we have to express this is as the horizontal projection of this angle on the vertical axis. So if we have an angle theta, then we have 3 feet, 1 minus cosine theta being the H max. So going back into my conservation of energy equation, we have 5 pounds times 3 feet times 1 minus cosine theta. So you have one equation, one unknown, right? And if we calculate things correctly, we have 1 minus cosine theta is equal to 0.00678. Theta is equal to 21.22 degrees. And that's it. So this is an example where you can have 2 different kinetic methods converging to solve a single problem. You should be able to do both of these for any problem. With some problems, you can use these methods alternatively, right? So you don't have to go with one or the other. With some of the problems, it's more convenient to use one of the methods rather than the other ones. So you really have to master which one is best and be good at identifying those situations, right? All right, well, I hope this was helpful, and I will see you next time.